Okay, hello everyone, and welcome to the week 7 tutorial questions, and we are going to talk about the bearing design life. So if you go to the canvas, you will find the list of the questions that we have there. Sorry, here it says week 5, it's not week 5, it's week 7. And anyway, you can see that the first question is going to be about the bearing life calculation. So here we are required to find, sorry, let me expand that. Okay, so required to find the expected life of the single roll bearings number 6018 if it was subjected to a load of 36,668 Newton. So before we get to start the solution process, we need to go briefly about the calculation for the life. So if I'm going to go through the slide that submitted to you, you will find that for design life section, first, we know that all the bearings have finite life, and eventually they fail due to the fatigue because of the high contact stresses. So the lighter the load is, the longer life of the bearing is, and vice versa. So the equation we're going to have for the bearing life is going to be the relationship between the load P and the life L. So the life L is going to be the number of the revolutions in million it can perform before the evidence of the fatigue in its any element. Now, the equation is given to you here. The L2 divided by the L1 is equal to the P1 divided by the P2 to the power K, where the K is a factor depend on the roller shape. Like, for example, it's going to be either ball bearings or it's going to be a roller bearing, including the taper bearing as well. So it's going to be 3 for the ball bearings and 3.33 for the roller bearing. Here the L is the life that you expected to have. L1 is the standard life. P1 is the standard load, and the P2 is the load you're going to apply. So with the C value, which is basic dynamic load rating, bear in mind the manufacturer's data can be used for the bearing selection, specifically the select of the bearing geometry and extra. The following list of the table 14s, are available for you to work on your design. It's going to tell you what the bearing number, as you can see in the first column here, and the diameter, and let me use the laser pointer. The diameters in millimeter and inches, that's for the inner diameter. Diameter for the outside ring, or what we call the outer race, and the width in millimeter and inches. Here we have the R, which is radius of the fillet we have for the edge. Now the other parameter is going to be the preferred shoulder diameter for the shaft and the housing. And finally, the bearing weight. And here we're going to have some performance parameters like the basic dynamic load rating and the basic static load rating. Now this copy, the black and white one, is only for the series of the 6200, and I got that from the old book. I got that for a reason. I don't remember what the reason is and why it's here. But anyway, that's the updated one from the 2018 version of the book. So again, you can see that the same information is going to be applied here. And we're looking mainly for the calculation of the dynamic load. And from there, we can find what will be the value for the static load. And then we're going to start to do the calculation for the forces can obtain. So again, first parameter is going to be find what is your shaft diameter and try to use the bearing that fit with the shaft based on the C value you are going to calculate. And that's what we're going to learn later. So here, the first table is going to be for the diameters from millimeter of 10 up to 17, 20 up to 40, 45 up to 60, 65 up to 80, 85 up to 100, 105 up to 130. So the standard bearings are available in several classes, typically the extra light, the light, the medium, and the heavy classes. And the designers differ in the size and the number. Designs are different in the size and number of the load carrying elements, like the size of the ball or the rollers and the bearing. The bearing number usually going to indicate the class, like the 6200, and the size of the bore of the bearing. Most of the bearings are manufactured with nominal dimensions in the metric units, and the last two digits of the bearing's number indicate the nominal bore size. So that's an example of relative sizes of the bearing that consider that we have the same inner radius for all these bearings, but the load value is going to be increased, and that's how the C is going to be increased. So this is the center line of the inner bore, and this is the radius of the bearing bore, the internal one. So if the load is going to be increasing, the bolt size, the width, and the diameter of the outer race will be increased accordingly. So you can see, of course, the thickness of the material, the mass of the bearings, everything will be changed accordingly. So that's what we have for the extremely light. This is of the 1900. Extra light is 100. The light is 200. The medium 300, and the heavy is going to be 400. The first example is the one that we had on the question sheet here. Okay, something similar. Just do it based on this example. Just write down the numbers here. We have 6018 is the type of the bearing, and the life we have here is 36,668. So here we have the catalog that lists the basic dynamic load rating for the ball bearings to be 31,358 Newton, rated for 1 million revolution. What would be the expected L10 life of the bearing if it was subjected to a load of 15,568? So now you can see that from here I can find the P1 and the L1, and I have the value for the P2. So I can apply the equation directly. Now we know the value for the L1, for the P1 and the P2, and the K value for ball bearing is 3. So I can simply apply the equation directly, and I will come to the point that the life 2 is going to be equal to the 31,358 divided by 15,600 and 15,568 up to power 3 multiplied by 1 million, and thus is going to give me 8.17 million revolution. So let's go back to the bearing we have, which is 6018. So I will go to the tables here and try to get some of the information we can make use of. So actually here we need to get the value for the C, and then from there we're going to start to calculate the life by using the second equation we're going to have. Anyway, we will grab some information from here, and then later we're going to go back and do the calculation. So we're looking for the 6018, 602, 3202. It's going to be somewhere here, 7, 8, 12, 16, 18. So 6018. Now, it's not mentioned actually, well, that's the one, and we're going to get the value for the dynamic C, which is 58,500. So I'm going to write down that somewhere on my paper, and we're going to use it later in my calculation. I'm going to show you actually this answer very soon, based on the equation we're going to use here. So 58.5 multiplied by 10 up to power 3, that will be number of Newton of the force C that we have. Now we go back once again to the calculation for the bearing life. This was the basic one. And then we go into the other equation, which is going to involve the C value. So now in this equation, we have the PD, we have the C, we have the K, and we can calculate the LD. Basically, if I can show you back once again, we have the C is 36,668, and I already found that the value for the P value to be 58,500 Newton. So the only thing we're going to do is put the C 58,500 and divide by the value of 36,668. Take it to the upper to the power over 3, and then multiply by 10 up to the power 6, and you will find the value for the LD. So if I'm going to do the calculation back with you, you will find that here we're going to have, as I mentioned, 58,500 and divided by 36,668. And I'm going to get this ratio. I'm going to take this ratio to the power of 3, and then I'm going to multiply it by 10 up to the power 6. All I can say is going to be 4 0.06 multiplied by 10 up to power 6. That's the answer for the first question. So when here advise that you spend 5 minutes on that, we spent less than 5 minutes on that. I did it longer because I tried to explain to you how to do these calculations. Now let's continue with the slide, and we're going to look for an answer for the second question on the bearing life, and it's going to be about bearing that required for the CNC machine shaft with a radial load of 3,333 Newton. So the P is going to be 3,333 Newton, and it's used for the CNC machine. The RPM value is given as 750 RPM. Okay, so we're talking about the value for the radial force, the RPM value, the CNC machine is the application, and we need to find what the value of the basic dynamic load rating C for the ball bearing. Okay, so now let's try to find the equation. I know the RPM, I know the load, and we need to find the value for the C. Now let's take a look to this equation. This one actually can be used to do this one, but I need to make a revising for this one, rearranging. So simply we can rearrange this equation to be C is equal to the PD multiplied by the LD divided by 10 up to power 6 up to power 1 over K. Now you'll say, okay, now how am I supposed to find the LD, which should be in revolution? This is not in RPM. So what we're going to do is going to be next, we're going to calculate the LD value, which is going to be equal to the H, which is the number of the hour that we expected that this bearing is going to be served, multiplied by the RPM number, multiplied by the 60 minutes per hour, and this will give me the life value. So now once again, take the parameters from here, and we're going to continue with the solution. We're talking about the load of 3,333 and 750 RPM, and it's for CNC machine. So let's continue with the work, and you can see that we have table 14.4, which is recommended design life for the bearing. Now our machine is, the application can be found here, and then we're going to find the design life. We're going to take either the minimum, or the average, or we can mainly take the maximum. That's what we're going to do. So first I'm going to look for my CNC machine, instrument, medical apparatus, okay, elevator, industrial fan, multiple gearing, rotary crushers, the cranes, a critical motor, industrial blowers, general industrial machines, conveyors. So it's a general industrial machine. And that's mean that the value for the life is going to be 30,000 hours. So again, to use that to do my calculation is 30,000 hours. And from there, we're going to find the value for the life first, and then we're going to find the value for the for the C, sorry. So let's go back to the previous page with the 30,000 hours. I'm going to start to calculate the LD. So bring the calculator once again. Okay, so we start with calculating the LD. 30,000 hours multiplied by the RPM of 750, and multiplied by 60 divided by H. So mainly we're going to have the 30,000 multiplied by 750 multiplied by 60. So we're looking at the value of 1.35 multiplied by 10 up to power 9. Okay, so this value is 1.35 multiplied by 10 up to power 9. That's it. Now, if I would like to do the calculation for this ratio, it's going to be 1,350 up to power 0.334, and then multiplied by the BD value of 3,300. So I'm going to do it as 1,350 up to power 0.3334. And then I'm going to multiply this value by the PD, which is 3,333 Newton, and this will give me 36,854 Newton is the answer, or 36.854 kilonewton. So it was easy question so far. We can do that in 5 minutes. Let's check the other one, which is going to be about the bearing selection. Now we have a single row deep groove ball bearing to carry 3,333 Newton of pure radial load from a shaft that rotates at 750, something similar to the previous example. Design life to be 60,000 hours. The bearing is to be mounted on the shaft with a minimum acceptable diameter of 46. The other question is select the single row deep groove ball bearing from the table 14 and 3 to carry the radial load of 10,500 plus whatever the value is. Now, we're going to work on this example, but with a different diameters, and I'll do the same thing here. And I would like you to actually practice on this one and following up the same steps. So that's for design life. Let me finish the examples here. That's something similar to the one we just done. Okay, and we can come to the answer here. Now we're going to, yeah, well, actually 1 million is achieved. Okay, now another way to calculate the value for the C is by using this equation, by using the life factor and the load speed factor. And this can be done by using the old chart from the old book that is not available anymore. And in this one, I can solve, for example, the previous question we just done with the, you remember it was something like 3,333 load. So, and the RPM value was 750 and the life was 30,000. So what I can do is I will come to this table, or this chart, sorry, and I'm going to find where is my 750 RPM. So I will go to, that's 500, 600, 700, 800, 900, and 1000. Okay, so 750 is going to be located here in the middle. So how to read this chart? You can see that here the lower, here the maximum. So that's mean that's 0.3, and this will be 0.32, 0.34, 0.35. So I'll say it's going to something like that, 0.35 for the value of the Fn. For the FL, for 30,000 hours, that's 20,000, that's 25,000, that's 30,000. So we're looking at 3.95 or 3.9. Well, that's 3.2, 3.4, 3.6, 3.8. So it's going to be something like 3.9. So I'm going to choose at 3.9. Now by having 3.9 and we have the Fn was 0.36, okay? By estimation, we can simply redo the calculation and find the answer. And that's actually what's shown here. And we said that we are going to find the same answers like we done in the previous example. If I'm going to get the value for the FL and the Fn, and then simply I'm going to apply to this equation, and we'll get a similar answer to the case if I did it the long way. Well, depend on you. Which one is long way, which one is short way? It's going to be your choice, not my choice. Okay, and you'll come to the answer that's going to be something like just 100 or less than 100, something like 70 a Newton difference in the terms of thousands. Okay, so that's it for the first two questions. And once again, you are going to do the selection of the bearing question based on the example I'm going to show you in the next video.